Hey everyone, today we are going to present our recommendation microservice performance study of BuzzBlog, which is based on the WISE project. Did it ever occur to you that some requests take seconds to return, but the majority returns in milliseconds? This kind of long-tail latency happens to a small yet non-negligible number of requests when resources are actually far from saturation. It significantly harms the user's experience and causes huge revenue loss. Our project aims to observe the distribution of request latency by increasing the system variability through the recommendation surveys and relating the performance to resource usage logs. We aim to identify the long-tail latency and analyze the cause of it. WISE Toolkit is the research platform to study system performance. It has three main components: BuzzBlog, System Monitors, and Workload Generator. BuzzBlog is a microservice architectured Twitter-like social media platform. It applies modern microservice architectures where processing a single request involves many different services distributed across a data center. Traditional system monitors log in a coarse-grained time window. Tools et al. And our advisor from the toolkits enable us to record hardware resources usage in a fine-grained time window when incur little overhead. Netload is a workload generator we use to generate synthetic workloads that are representative of web-based applications.
The dataset we use in this project contains tweets scrapped from September 2009 to January 2010 by the man called Chen Cavalli Li on archive.org. However, the data is badly stored with multiple different delimiters and is saved as the TXT file, so we abandoned many bad data points. As a result, we extracted 8,977,164 tweets with user metadata, which we assume is capable of starting our experiment. When it comes to preprocess, we first remove baitlines such as lines missing user ID and tweet text at the same time. We then applied the common natural language processing technique leveraging NLTK Python library to do the preprocessing. So punctuations, stop words are removed, but we didn't stamp or convert words to their root form because we would use the most common words to mimic the recommendation system. We count the appearance of each word in the dataset and extract the most 100 frequent words as keywords. We borrow the concept from TF-IDF and NLP technique. The more frequent, the more important. Also, we created 50 words that do not exist in the dataset with the help of randomwordgenerator.com for this experiment.
We add a recommendation microservice to BuzzBlog App. The existing database in BuzzBlog are SQL-based databases. Given the growing popularity of non-SQL databases, we decided to use MongoDB so that we can study the performance of non-SQL databases. Our recommendation service supports searching a keyword specified by the user and returning relative posts that contain the keyword. We make use of Mongo CXX library to integrate the Mongo query with our CPP service. In order to better observe a diverse latency distribution, we add two parameters to the query to add variance in response time. The first is search size, which is the number of posts to search before stopping searching. The other is return size, which is the number of posts to return. We also add to the API gateway to enable HTTP endpoint for our recommendation requests. We save these functionalities to different Docker container images, which will be easily to pull from experiments. In order to run experiments on our recommendation microservice, we also configured a load generator and a controller. AT load generator from Wise Toolkit can generate workloads that are representative of web-facing applications. We use it to generate HTTP requests. We construct each request using a random keyword, a random search size, and a random return size. A controller should install the experiment environment and deploy experiment containers automatically. We configure the workload from the controller, including experiment duration, sessions throughput, and request graph. In order to achieve a micro-testing involving only our recommendation service, the request graph, as shown in Figure 1, has only one state and goes to itself with probability 1. We also configure system parameters, including which node to host which service, as well as Docker deployment configurations. We run experiments on Cloud Lab. We use Cloud Lab to build our own cloud. Our cloud is composed of 4 nodes. Controller and load balancer live on node 0. According to the system parameter configuration, the controller will deploy to node 1 a load balancer container and an API gateway container. It will deploy to node 2 a recommendation service container. It will deploy to node 3 a recommendation database container. It will start system monitors, including collect TL and R-advisor on all the nodes. We ran experiments with a duration of 12 minutes, with the first minute to ramp up throughput and the last minute to ramp down. Here is the experiment results when throughput is set to 10. Figure 1 shows the latency distribution of successful requests. The x-axis represents latency in seconds, and y-axis represents the frequency. Figure 2 shows the number of requests per second over experiment duration. Figure 3 shows the latency of requests over time. We can see from Figure 1 that when the throughput is low, most requests are handled in sub-seconds. You can see from here, it's less than 1 second. We can notice that, interestingly, there is one request that takes more than 5 seconds. Here it shows. From Figure 3, we can infer that this request happens at around 20 seconds. Should be this request. This line represents that request. However, from Figure 2, we can see that the throughput at that timestamp is just normal. There is no surge at that timestamp. We show another experiment result when throughput is set to 50. The 3 figures show the same thing as before. Most requests still finish in sub-seconds. From Figure 3, we can see that most requests have latency of, here it is 10 to the minus 1 seconds. However, there is a more diverse distribution as shown in Figure 1. And from Figure 3, we can see that most of them occur near the end of the experiment. Still, we can see from Figure 2 that the throughput at that time is just normal, around 50 as set in the configuration. We think the long latency starts might be because the hardware resource usage is near saturation at that point, and it is propagated from then on to later requests.
One purpose of the exploratory project is to find out if there are any potential factors of latency. In other words, we want to find things that could be optimized. If we find some bottlenecks and successfully reduce the whole running time by 3% on a single machine, we actually reduce tremendous workloads for the service with a large scale such as Twitter. To examine what happened on CPU in the experiment, one way is by the Linux tool perf to profile a CPU. The perf record shows a function called tree summary with the percentage of time in each code branches with details, which is good, but the report is super long, and with the example on the Flamegraph website, a 90-second experiment might require me 3 days to read through the whole report, which is impossible in reality. Fortunately, we have Flamegraph. This is the Flamegraph from our experiment on Node 3, the database node, with throughput setting at 10. The horizontal shows the proportion of the process in this experiment, and the vertical shows the stack of processes. So because this is an exploratory project and the following interpretation of Flamegraph are based on my understanding, if there is anything incorrect in this part, I would appreciate if you could let me know in the QA session or leave a message in the chat. So I click the process TCP live BPFCC. A typical pattern that something could be optimized would be like this high tower with a plateau at the top. So if I click it, we can see that this this function libBCC so that is actually walks through a lot of function code to reach that, and this is the pattern that might be something interesting to optimize. In order to compare the CPU profiles among different throughputs, we generate Flamegraph at throughput 10, 50, and 200. To easily find the potential inside 10 and 200 are used to generate a differential Flamegraph. Differential Flamegraph is a specialized Flamegraph to compare two records. In this example, we compare throughput 10 and 200 on the graph of 200. On the graph, red means that the samples increase from throughput 10 to 200. We can understand it as this function requires more time when we are at the throughput 200. On the other hand, blue means the sample decrease. Because we use Mongo in this experiment, I searched for MongoDB on Node 3 Flamegraph, but I found nothing on this graph. I assume they might be profiled as unknown, or then simply live inside the Docker process. So that might be a reason why I cannot find those keywords. And this situation happens when I search for string like TCP, send, push, request, etc. on the other nodes. So I did some research, and there might be some ways to recode a process inside the Docker. However, that requires some other overhead, and this overhead might impact the result of perf. So additional experiments might be needed to explore this. This is our work distribution reference. Thank you.